Hello, my name is Stephen Baek. I'm an associate professor of data science. I also have a courtesy appointment in the Department of Mechanical and Aerospace Engineering here at the University of Virginia. Today, I'm going to be talking about my research topic, which is called a geometric data analysis. So, to get started, let me use pasta as an example, because pasta is probably something that everybody loves. What I like about pasta is there's so many variety. There are different shapes. Some are ruffled, some are straight, some are thin, some are thick. Some has little crannies and things like that. And what's so interesting about those different shapes is that they create different texture. They create different flavor. And then when you match them well with right ingredient, then you can kind of boost, the flavor of the dish, right? So, as a scientist, I find it very interesting and fun to experiment with different types of pasta, with different, types of noodles, different ingredients, and things like that. So that's basically the story that I'm about to tell you, because not only pasta, but there are many different things in our world where certain properties, certain scientific quantities are defined by geometry, similar to how the geometry of pasta determine the flavor and the texture and the overall, sensation as you enjoy the meal. So. Before I get started, this is the work done by largely my students and postdocs, who's been amazing. So let me first shout out to them for their amazing work. So back to the story. My research is about geometric data analysis, and this is essentially what me and my group is doing all the time. We're playing with different shapes. We try to match them. We try to compare them. We try to retrieve them, and so on and so forth. To do what? In order to develop some scientific intuitions. So the main kind of the unique feature about geometric data analysis from other types of data analysis technique is that in traditional data science we've been talking about tables basically. So you have lots of numbers, sort of stored and organized in the format of an Excel sheet, basically. So here I brought this example from MLB. I'm a huge fan of baseball. So we see this, all these amazing players with their names, with their age, the team, the league they played in, how many games they appeared, the hitting average, how many home runs, how many doubles, triples, all kind of informations are stored in this kind of table. So usually in data science, we're talking about rows and columns. So a row represents a data sample, which in this case, a player. And then column basically represent a variable or a parameter that describe that row. So what are the numbers that describe a baseball hitter? Could be the number of home runs, number of triples, average at bat, those kind of things would be the numbers that describe the performance of an individual player, right? So rows and columns was the traditional format of data set. However, we're living in the 21st century, and with the advancement of sensors and cameras and a lot of different things, we started to collect a lot of interesting data that doesn't necessarily fit into that rows and columns format. So consider an example of an autonomous vehicle. Autonomous vehicles, one of the enabling technology to allow them to like drive themselves is this sensing technology called LiDAR. So LiDAR is essentially a three-dimensional scanning technology that works in real time. Not only autonomous vehicles, but if you have Roomba in your household, Roomba also has the LiDAR sensor to sense the space around the robot so that the robot can, the robot knows where to go and where to, suck up the dust and, things like that. Now, if you think about it, the way that LiDAR works is basically it samples the XYZ coordinates of various different objects in the world, right? So you sample lots of points and their XYZ coordinates, from the road, from your house, so that this autonomous vehicle or the autonomous robot can know, what it looks like, what the world looks like. Now, the tabular organization, tabular structure of such XYZ coordinates may not make a lot of sense if you think about it, because at the end of the day, it's going to be a bunch of rows of XYZs. And then from those rows and columns, you cannot really infer anything meaningful because the reason why those geometric data, the LiDAR sensor, can help robots to see the world is because those data points actually have some spatial structure. So simply just listing them line by line is not gonna give you any interesting information. Consider medical imaging as another example. Nowadays, I don't know how many of your parents who are watching this video, but nowadays you can, see the face of the baby using ultrasound, and then they can even three-dimensionally reconstruct the facial shape of the baby. So it's kind of a cool technology. I did the same thing for my daughter several years ago, and then it was really fun to really see the three-dimensional shape of the baby. It was so exciting as a parent. But again, if you think about it, at the end of the day, this ultrasound, CT, MRI, those kind of three-dimensional imaging technology will collect XYZ coordinates of something, part of your body, and then it will somehow spit out the collection of those XYZ coordinates. Again, if you just list them, line by line, there's not going to be a lot of geometric meaning. There's not going to be a lot of interesting patterns emerge. Those XYZ coordinates are only meaningful when you have that geometric structure spatially, lined up. One last example, smartphones nowadays, three-dimensional scanning and things like that is actually not a technology that is far, far away from now. Nowadays, like the new version of iPhone has this three-dimensional scanner basically, and that's how your phone recognizes your face. So each time you unlock your phone, what happens is there's some three-dimensional scanning technology scan your face. And then based on that three-dimensional scan, your phone will recognize if you're the real owner of the phone or not, right? So we're not talking about a technology that is only applicable to some fancy medical imaging devices or some fancy autonomous vehicles that are far, far away from our real life. We're talking about a technology and type of data we collect almost every day. So with that introduction, I'm gonna show you some examples because I don't want to be like too much up in the air and too abstract about it. So let me give you some examples of how this geometric data analysis can be applied. And the first example I'm gonna use is the study of body shape that me and my collaborator has conducted a few years ago. So body shape matters, what it is about. This is actually a paper that we published recently in a journal, and then it got really viral because it was right after COVID, and then everybody gained some weight. And then, there was a lot of interest about this article. The main message from this paper was that there was some unfair bias associated with people's body shape in the socioeconomic market. So in a very, very, rough summary, the conclusion was that if you're a man and if you're 1 centimeter taller than the others, then you are likely to earn about $1,000 more in terms of the annual family income. And if you're a woman and you have 1 unit lesser of BMI, then you're likely to earn about $900 per year in terms of annual family income. So how did we analyze all this? The interesting thing about this research is that we had an access to a database of 2,400 North Americans. We had this three-dimensional body scans of those individuals alongside some survey results revealing their demographics. So we had the three-dimensional scans alongside the table of their demographics, what's their income, what's their level of education, what kind of car they drive, what is their jacket size, what is their shoe size, and all kind of informations were available for those 2,400 subjects. So what we've done was to mathematically analyze the distribution of those three-dimensional body scan data and then correlated that with variables that reveals the socioeconomic status of those individuals to see if there's a correlation. We use a technique called geometric autoencoder. It's basically an artificial neural network that is specifically designed to be able to analyze the three-dimensional geometry. So as opposed to other types of neural networks, which expects basically a table grid of numbers, this particular type of autoencoder can handle XYZ coordinates that are spatially distributed in a very specific geometric manner. So I'm going to skip all the mathematics, but at the end of the day, what this autoencoder gives us is the representation of the body shapes. So it gives some numbers that we can use to characterize different body shapes. And then what we've done was to correlate them with other socioeconomic parameters, such as family income in this example. So long story short, I'm going to just be brief about the result. There's a lot more in the paper, so if you're interested in, please go check out the paper. But one of the main findings from this paper was that there were certain relationship with body shape and the socioeconomic outcomes of those people, which is indicative of the fact that there's some unfair bias that we apply to people with different body shapes. So like I said earlier, in case of men, there was a preference on the people with a taller, height. And then for women, there was a preference, on, skinnier women compared to, to the other body shape. So on the chart, you can see that, well, first of all, education and experience seems to be, one of the, most predominant factors. So I think a good thing for especially audience who are still in college, trying to justify why you're paying, tuition to be in college. Here's an evidence that you should be happy about, right? The more you stay in school, the level of education has a very strong correlation with your income in the future. So that's a good news for those of you who are in college. But compared to, the other things, body shape had actually a very strong correlation, as much as other variables like education. So that was kind of a striking result from this analysis. Before we move on to a different example, let me tell you a fun story. So another thing that just out of curiosity that we tried was to compare the reported body heights, reported body measurements versus the actual measurement from the 3D scanning. So what I mean by that is when the subjects, when they were 3D scanned, they not only filled their survey questionnaire about their demographics and socioeconomic status, but they also reported their height and weight. So we have this three-dimensional scan, which I would say is more accurate. And then we have the reported height and weight associated with those three-dimensional scans. So we thought it would be interesting to take a look at the reporting error, which means like how many people were inaccurate about reporting their height and weight. So here's a chart showing the reporting error in height for both male and female subjects. And then the zero line, the horizontal line here, means there's no error. Every reporting was accurate. And then if you go above that line, that means people sort of reported to be taller than their actual height. And then if you go below zero, then that means people kind of underreported their height than the actual of their stature. And then the dashed lines over here, before we go to the dashed line, the bald line is basically the average of the reporting error as a function of their actual height. So the horizontal axis is their actual height, and then the reporting error is represented as a black bald line here. So you can see that everybody in general likes to report their height a little bit taller than what it is actually, which is about 20 millimeter. So that's roughly less than an inch, I would say. So slightly exaggerated reporting was observable in the data set. And then the dashed line is basically what we call 95% confidence interval. So basically, that's the statistical variance. Some people, add more to their actual height. Some people add less to than their actual height. And then the 95% confidence band basically shows the range of such variations for the majority, 95% of the population. So with that being said, if the dashed line is significantly above zero, that means there's a significant trend of over-reporting. And in case of men, obviously, there's a huge trend of over-reporting their height compared to women, where the lower bound is kind of touching zero. So there's no, significant, over-reporting trend that we can conclude from the female data set. But in case of male, there was a significant over-report. So it says 6 feet tall in my driver's license, and there's a good chance that I was lying to in my driver's license. Here's a similar chart for the body weight. Now the trend is a little bit different between male and female. So an interesting thing is, in case of height, everyone was just over-reporting. Now in terms of weight, people who are skinnier, on the skinnier side, have a tendency of over-reporting, which is why the left-hand side of the graph is way above zero. And then people who are, more obese, they tend to underreport their weight. And then as you can see, for both male and female, there was this trend of going from the left top to the right bottom, which means that, people who are, less heavy tend to over-report their body weight. And then people who are overweighted tend to report less than their actual body weight. In case of male, that slope was very steep, which I think is sort of indicative of our stereotype in our society that man has to have certain, physique, if you will. But in case of women, interestingly, the trend was almost uniformly below zero, which means almost everybody was underreporting. And again, I think that's an indicative of this stereotype in our society that, if you're a woman, the skinnier, the better. So that was an interesting find, from this research. So all of this actually supports our, initial observation that there was some differential preference in terms of people's body shape in our socioeconomic market. And it was actually a fun result to take a look into, although the implication was not very positive. Now, that whole research was about the beauty premium, per se, in human body shapes. But what about other objects? So tumor, for example. So this is kind of a similar line of research where we investigated the shape of cancer cells in correlation with their survival probability. So the motivation for this research was this myth or some empirical observation in the medical community that if you have a tumor that looks round and nice in the image, then your chance of survival, your chance of treatment success is going to be higher. Whereas if you have a tumor that has fuzzy, irregular, spiky, ugly boundary, then your chance of survival is going to go significantly down. And that is something that almost every clinician say from their experience. So as a data scientist, I was curious and I wanted to see if there was any quantifiable trend. And I thought that was a perfect example where geometric data analysis could be applied. So same figure basically, right? Now instead of the space of human body shapes, imagine there's a space of all possible tumor shapes. And then there's got to be a trend in terms of how easy or difficult to treat this tumor cells. So we collected a lot of data that has CT images and of cancer patients. And then what we've done was to analyze their shapes using what is called a convolutional neural networks. It's a deep learning model that learns to analyze complex image patterns and then derive a conclusion. Again, I'm not going to go into too much of the details, but one of the trends that we found was indeed that there were very strong correlation with the tumor geometry and the survival outcome of the lung cancer patients. And the correlation was strong enough such that only with the shape of tumor, we did not even use the other medical histories like a smoking history and things like that, which are known to be very strongly correlated with the survival probability of lung cancer patients. We did not even use them. Just from the shape alone, we were able to make a actually pretty good prediction of whether or not the lung cancer patient is going to survive after 2 years, which is the 2-year overall survival in this chart. And then after 5 years, which is the 5-year overall survival in this chart. And as you can see, just from the shape, you can already make a pretty good prediction. We have kind of cross-validated this against other data sets collected from different hospitals, and strikingly, the trend was similar across different data sets. But another interesting thing that we figured out from this study is that this geometric data analysis technique allowed us to discover markers that were more interpretable and explainable to human eyes. So one of the main criticisms on deep learning and convolutional neural networks is that they have millions or sometimes billions of parameters. And what that means is your model can, if you beat it up hard, your model will say whatever you want it to say. Because models with large number of parameters can very easily overfit to the training data set. So when you don't have a large enough data set, your model will just draw a trend line in a way that, sort of go through that, but doesn't really generalize to unseen populations. So that's what we call overfitting. And neural networks, especially deep neural networks, are very easy to overfit. And what that means is, even though in terms of the prediction accuracy, you may have a pretty good, prediction accuracy, if you look inside, neural net may make a reasoning that doesn't really make any sense physically. So here's snapshots of the features that are learned by the convolutional neural network. The first two lines are the features from our work, and then the one at the bottom is a deep learning model from somebody else's research, and then we tested that on our data set. And as you can see, on our approach, we have a lot more interesting shapes going on, whereas unfortunately, the bottom one has almost like a random jumble of noises. And the reason for that, we believe, is that we use this idea of geometric data analysis instead of just directly applying convolutional neural network. We actually had a structured approach of learning those geometric features. And as a result of that, we believe that we were able to do a better job in capturing those meaningful geometric features. And this is something that I'm a little careful to say in front of the camera, because there's still a long way to go to validate these claims clinically and then confirm this initial findings. So don't take what I say as is, but from our initial exploratory analysis, the features that are captured by the neural net was actually quite meaningful. So if you look at that C37399, which is the one on the right top corner, you can see a big blob, and then at the bottom there are two little blobs. That is actually a blood vessel going underneath the tumor, and it just happens to be, a sliced visualization of a three-dimensional geometric feature. So when you render that in 3D, you can actually see a blood vessel coming right underneath that big blob, big circular object. And then what we are, the way that we're interpreting this right now is that probably the neural net is looking for blood vessels and lymphatics that goes nearby the tumor. So the big block is probably a tumor, and then the tube-like shape below might be blood vessels and lymphatics. And neural net actually thinks that that kind of geometric structure may have a strong correlation, strong contribution to the lower survival rate of cancer patients. And that physically kind of makes sense, because if you have tumor nearby blood vessel, for example, blood vessel is a kind of a highway for nutrients to flow, right? And if the tumor is nearby blood vessel, that means that you have an easy access to nutrition. So from tumor's perspective, it is easier to grow, right? So if you get to see that kind of features in cancer patients, that means there's a good environment for a tumor to grow, and therefore, clinically speaking, it is going to be harder to treat. So that is just one example of many other interesting geometric features that are found by this approach. So our next step is basically to clinically validate those claims. Like I said, this is still kind of an early stage analysis, but we're kind of excited about this possibility opened up by this new geometric data analysis technique. Again, similarly, this is kind of an early exploratory analysis in terms of the cancer survival. And here we have this sort of like a heat map showing what are the areas in the CT image that may have some interesting geometric features that contribute to the growth of tumor and the overall survival rate of the cancer patients. Again, it's an early stage analysis, so there's not a lot to conclude at the moment, but we're also excited about this possibility of using this kind of heat maps as a way of telling and helping doctors in terms of where to look at and where to treat. Because in some subsamples in our data set, we show the correlation with this heat map with the progression of the cancer patients. So again, it's still early to conclude anything, but there is a chance that the neural net may be looking at the potential sites of progression of the lung cancer patients. Now, let me switch the subject a little bit, something a little more exciting than cancer, which is the application of material design. So at this point, you probably realize my research group is sort of all over the places. We started from some social science research, and then we moved to medical research, and then here we are in material science. Especially today, I'm going to be talking about this thing called HMX. HMX is an explosive that has a variety of use, not only in military, but also in civilian application. One of the civilian applications of HMX is the oil well development. So when you discover, the fossil fuel underground, and then you want to drill a hole, HMX is one of the key enablers to, drill the hole so that you can access to the oil. Here's another fun example. JAXA, I hope that's how it's pronounced, but that's the Japanese NASA. And in their recent space mission called Hayabusa 2, that's the name of that satellite-looking spacecraft. And what Hayabusa 2 did was to destroy to sample some rocks from asteroids so that they can use it for space research. And then in that mission, they used HMX to basically drill a hole through the explosion, and then they were able to sample some of the loose soil as a result of that explosion. So those are the examples of HMX. Now, one of the issues with HMX is it is very, very sensitive, which means even a small shock impact applied to HMX may result in a detonation, which is not good from the safety perspective. So one of the things that people want to do is to make HMX more safe, meaning less sensitive, so that we can handle these materials in much safer fashion. But in the meantime, you don't want to make it too insensitive, because then, when it is supposed to blow up, it will not blow up if it is too insensitive. So there's, finding this subtle, value of sensitivity and engineering the material in that way is one of the scientific mission of the research community here. And in order to do that, people run a lot of simulations. So what you're seeing up here is a computer simulation of how the detonation happens. So let me, unpack this a little bit. So there's a shock coming in from the left to right on your screen. And the shock is basically what induces the collapse of those HMX structure. And then as a result of the collapse of those structure, what happens is it releases a high, chemical energy, and then the temperature goes up significantly. And then you start to develop what is called hotspots, which are the red blobs that shows up in the video. And knowing the rate of hotspot formation and then how fast they grow is a critical thing for engineers who wants to engineer the sensitivity of HMX materials. So what people do is basically to design a lot of different materials, they virtually explode them, and then they basically count their, how many hotspots are there, how fast they grow, and then they try to find the relationship. Now, the interesting part about this is as much as the chemistry, the geometry of this microscopic, the material image plays a significant role in the formation of hotspots. And what the community has figured out so far is that those little cracks and pores in the microstructure is basically what you see under microscope. So if you have an HMX, you look at it under microscope, you will see lots of crystals and cracks and pores and things like that. And the community so far have discovered that the geometry of those pores and cracks are the critical parameters that determines the detonation behavior of HMX materials, and not only HMX, but other types of explosives and propellants. Now, if you're an engineer who's interested in engineering the sensitivity, then what you would do is to control the size of the pores, the porosity of the material overall. You may want to control the crystal shape and a lot of different things. And then you may want to observe what such change leads to in terms of the hotspot formation, which means you'll have to generate a lot of different microstructures and then simulate them on computer. And each time you do that simulation, now you have data points showing the relationship between the microstructural geometry and the complex thermodynamics. Now there's one problem. The problem is that each of such simulation takes about a day on a supercomputer. So we're not even talking about some laptop or some commodity computing environment. We're talking about a supercomputer that is hundreds of times faster than the ordinary computers. And even on those powerful computers, it takes about a day to run those simulations. So if you're a material scientist, you have this nightmare where you have to wait for several months, and then you still have less than 100 data samples at your hand. So if you're interested in exploring the relationship between the geometry and the thermodynamics in a data-driven way, then what that means is you'll have to wait for several years to collect enough of data. And even after that, the total number of data available to you may not even be sufficient to discover that complex relationship. So that's where machine learning and data science can come in. What my group has done was to develop this thing called a physics-aware recurrent neural network. Long story short, this is an artificial neural network that is specializing in analyzing the microstructural geometry, and then it can learn the physics equation that governs the thermodynamics of the hotspot evolution. Again, there's a lot of big words there, so I'm not going to go too deep into this. But what this can do is, for a given microstructure, we can simulate we can predict the hotspot formation and the growth pattern without having to go through this direct numerical simulation, which takes about a day on a supercomputer. So here are some examples of neural network predicted physics. And as you can see, the overall distribution of hotspots and then their growth rate is very similar to those that we obtain from some complex physical simulation. And quantitatively speaking, we found that the values predicted by this Park model was actually very comparable to the direct numerical, the complex physics simulation. But in terms of the computational speed, there was a significant improvement. In case of Park, on a commodity laptop, we were able to run the code in less than a second. So compare that with a very expensive simulation that takes a day on a supercomputer. Now we're talking about, less than a second prediction of fairly accurate physics on commodity laptops. So we can scale this up, and hypothetically, we can generate, hundreds or thousands of prediction results every day, as opposed to having to wait for a long period of time. So this will accelerate the material research quite a bit. And eventually our mission is to enable this kind of applications where engineers tweak the microstructure geometry and then see the response in terms of the hotspot formation and growth rate. So here's just one very simple example comparing the HMX materials with smaller size crystals with a bigger size crystals, and then we can see that there's a different patterns of growth. So this kind of research is what we can enable by having that kind of machine learning approach. Now, speaking of tweaking the microstructure, we're using this technique called generative adversarial neural network, which I think you're already probably familiar with the name of deepfakes. So deepfakes on the internet, people generate all kind of crazy photos. They create pictures of some fake, people, or they also create, I don't know, all kind of interesting photographs of cats riding a horse, or something like that. But we're using that deepfake technology for the scientific progress of the material science community. So what we're doing with that same technology is to generate the synthetic microstructure images using the same deepfake technology that people use to generate faces. Now, what that enables is the ability to control the microstructure in a way that we want. So in this example, we just turned a knob, quote unquote, to increase the size of the crystal or decrease the size of the crystal. And then by giving knobs to turn to engineers, they can more effectively generate some, virtual specimen for their virtual experiment. And then, we have this, we can basically explore this vast, design space of materials of those microstructures of those materials. So we can vary the size, we can vary the orientation. And at the end of the day, what that enables is the ability to automatically conduct experiments in the virtual space. So with that deepfake technology, we generate lots of specimen. And then for each of those specimen, since now we can estimate the physics less than a second on a laptop, we can run lots of predictions on those different material specimen. And then we'll be able to predict the physical properties of those materials. And if we can do that in a fast enough manner, then we'll be able to explore the design space in relation to the material property. So as a result of that, material scientists will be able to discover materials that has the targeted material properties in much efficient manner. So that's kind of the long-term vision that we're heading towards, and we're actually making pretty meaningful steps towards that goal, thanks to a lot of amazing graduate students and postdocs that I'm working with. So in conclusion, shapes play an important role in many different areas of science. We talked about the human body shape, which is sort of related to social science applications. We talked about medical application of geometric data analysis. We talked about material science. And there are actually many other areas that we're applying this geometric data analysis idea to solve the problem, because in our world, there are many problems where shapes is one of the most critical variables that governs some scientific phenomena in that domain. So being able to collect more geometric data opens up a lot of possibility. And then in that trend, I think this geometric data analysis can be a key to harness all these advances in sensor technologies, all the scanners and fancy cameras and things like that. And like I mentioned earlier, there are lots of applications, not just in those three areas that I used as an example today, but also there are many other areas that we can explore. So if you're interested in doing this kind of research, you're more than welcome to reach out to me. I'll be happy to chat about it. But yeah, thank you so much for my opportunity to describe my research to you. And I hope you guys enjoyed.